Lesson number 2, let us talk about methods of verbal proofs. So this is just a recall because you have learned this already in mathematics for the modern world. At the end of this session, you will be able to demonstrate an understanding of the concept of arguments, formal proofs, inferences. Use truth table to determine an argument's validity. Recall rules of inference and rules of replacement. Express arguments using logical symbols, and construct a formal proof of validity of an argument. What is an argument again? An argument is a finite sequence of P sub 1, P sub 2, up to P sub n, Q of statements. The statements P sub 1, P sub 2, up to P sub n are called the premises of the argument, and Q is its conclusion. Let's take, for example, I have this sentence. If I like you, then I will marry you. So this is just if P then Q, just a proposition. We have the premise, I like you, and our conclusion, I will marry you. But when we say an argument, example, if you are rich, if you have car, if you're handsome, if you're tall, then I will marry you. In this case, we have how many premises? We have 4 here in this given statement. This 4, you are rich, then you have car, you're handsome, you're tall. Then I will marry you. Then I will marry you is your conclusion. So these are your P sub 1, P sub 2, P sub 3, up to P sub n, and this is your Q, therefore Q. These 3 dots, like a triangle, you read that as therefore, in short then. Example number 1, consider the following argument. If Nana solved 10 programming problems correctly, then Nana obtained 100%. Nana solved 10 problems correctly, therefore Nana obtained 100%. So first step, you need to make a representation. Each statement that can stand alone, represented by letters starting with PQ, they are propositions. So let P be the statement Nana solved 10 programming problems correctly, and let Q be the statement or proposition Nana obtained 100%. And then you will read again our given argument and translate into symbol using connective. So as we read, if Nana solved 10 programming problems correctly, then Nana obtained 100%. So ayan, if P then Q. You know the symbol of if then naman, diba? That's arrowhead pointed to the right. Then another sentence here, Nano solved 10 problems correctly. It stands with letter P. So nakalagay na pangalawang proposition P. Then therefore, Nano obtained 100%. Therefore, Q. So that is our argument in symbol. Another example, consider this parallel argument. If Kier solved 6 Java problems correctly, then Kier obtained 80%. Kier obtained 80%, therefore Kier solved Java problems correctly. Again, let us make representation of each statement that can stand alone, or you call them proposition. So let P be the statement Kier solved 6 Java problems correctly, and let Q be the statement Kier obtained 80%. Symbolizing them using connective, if then, arrowhead pointed to the right. Reading again the original argument, if Kier solved 6 Java problems correctly, then Kier obtained 80%. So if P then Q, Kier obtained 80%, so that's Q, therefore Kier solved 6 Java problems correctly, therefore P. Ayan, so that's how you translate. And then we have rules of inference. We will recall this. We have 9. And rules of replacement, we have 10.
So let us discuss the different rules of replacement. So number 1, De Morgan's. In De Morgan's, we have this formula, not P and Q is equivalent or is congruent to distribute not to each of the propositions inside the parentheses. So not times P, not P, then N will become or, not times Q, not Q. And vice versa, if I have not times P or Q, just distribute the not times P, not P. Then OR will become N, not times Q, not Q. So that's it. If you see the left side, you can replace that by the right side. And if you see the right side, you can replace that by the left side. That's why we call this rule of replacement. Number 2, we have commutative. Shortcut COM. Okay, so we have this formula. If we have P and Q, it is just the same as Q and P. It means that the order of the propositions does not affect the results, even you interchange them. As well as if we have P or Q, it is just equal to Q or P. 3. Associative. So in short, ASOC. So it means from the word associate, so the grouping. So we're talking about grouping of the propositions. So we use the grouping symbol, parentheses. Let's take for example, if you have P or Q or R, it is equivalent to P or Q or R. If you notice in our left side, we group the second and the third, or the last two propositions, and on the right side, we group the first two propositions, and they are just equal. Likewise, if you have P and Q and R, it is equivalent to P and Q and R. So the grouping of the propositions does not affect the result. So at the left side, we group the last two, and at the right side, we group the first two. So that's associative. Number 4, distributive. So you will just use this when you prove. Let's recall algebra. If you have 3 times x plus 5, we will apply distributive property. So distribute 3 to each of the terms inside the parentheses. So 3 times x, 3x. Then copy the operation of plus sign. Then 3 times 5 is 15. So in mathematical logic, if we have P and Q or R, just distribute P to each of the propositions inside the parentheses. So P and Q, P and Q. Then the plus sign is like the OR, is equivalent to OR, then distribute P to R. P and R, so P and R. Also, if you have P or Q and R, just distribute P to each of the propositions inside again. So P or Q, P or Q, then copy the symbol N, then P or R, P or R. 5. Double negation. So in short, DN. If you have P, this is just equal to not P. It's like in integers, if you have 8, it's just the same as negative times negative 8. So negative times negative 8 will become positive 8. Number 6, transposition. In short, trans. So if you have, if P then Q, it is just equal to not Q then not P. Let's recall transposition in algebra. If we have 3x minus 4 is equal to 5, we need to solve for x. So bring down 3x, then bring down 5 at the right side of the equal sign, then transpose negative 4 to the right. So as you transpose, it will become 3x is equal to 5 plus 4. So what happened? We changed the sign. Then combine terms. So 5 plus 4 is 9. Divide both sides by 3. So cancel 3. So x now equals 3. So it means that when you transpose, you will change the sign. If that is positive, it will become negative. If that's negative, it will become positive. Number 7, material implication. When you prove, you will just write IMPL. So the formula is given by if P then Q, it is just equal to not P or Q. Okay? So if you see the left side, just replace that by the right side and vice versa. Let's say, for example, if R then S, it is just the same as not R or S. So we just follow the pattern or the formula or the rule. As well as if P then Q then R, it is just equal to not if P then Q or R. So I will not use number 8 formula, material equivalence, and number 9 exportation in proving. So we will proceed to number 10. So in number 10, we have tautology. So just use this abbreviation, taut. If you have P, it is congruent to P or P, and also it is congruent to P and P. So if I have R, this is just equal to R or R, also equal to R and R. Rules of inference. I will discuss the last 3 rules. Number 7, simplification. Abbreviation, we will use SIMPT. Let's say, for example, you're in a relationship. You are P and your boyfriend or girlfriend is Q. And then your girlfriend or boyfriend leaves you or fully you. So what will gonna happen? Therefore, you will become single and forever alone. So this Q will be removed and what's left is just P. Number 8, conjunction. Conj. So in number 7, in simplification, you will just subtract. So you use the symbol connective N when you want to subtract. So in conjunction, the formula is given by, so here is you're single, and you travel, you become joiner. You meet somebody or someone, and that someone is Q. Then you talk the whole night. Then you're click. Therefore, P and Q. So you become lovers. So in conjunction, if you see a single proposition and another single proposition, you can combine them by using the symbol n. Always remember, when combining, just use the symbol n, only n. 9. Addition. Abbreviation, add. Here are you. So you're happy, you're in a relationship, but there comes a point that you're bored. So you will become two-timer. You will add another girlfriend or boyfriend. So you're a two-timer or a double crosser. So whenever you add, you will use the connective or. Always remember, in addition, just or is the symbol you're going to use when you want to add another proposition. So I will discuss now the first three in the rules of inference. Number 1, modus ponens. Empty. So the formula is given by, if P then Q, P therefore Q. So you have two premises here, and this Q is your conclusion. It means that these two premises is equal to this one conclusion. You cannot conclude Q unless you see P, then Q, and P. Let us make an example for modus ponens. So here at our right side, you can see here a two-column table. It's like in geometry, we have in the first column statements and in the right column reasons. As you recall, in geometry, we have encountered lots of proving in that subject when we were in junior high school. So it's like, if you have angle A is congruent to angle B, what's the reason? Diba? We will write given. So in here, numbers 1 and 2, I will write premise. It means they are just given already, no need to prove. So in here, from 3 to 6, you need to prove the following by stating the right reason. The reasons are the rules of replacement and rules of inference that I already discussed to you. So in number 3, if P then Q, what's the answer? What's the rule that we are going to apply? If you will recall the rules of replacement, you can find this number 3 in material implication formula taken from number 1. So the answer here is from number 1, IMPL, material implication. Number 4. So how we ended up with this given P and Q. As you know this, it is taken from number 2, Q and P. What's the relationship between numbers 2 and 4? The order changes. So it means we will apply the rule commutative. So from number 2, our reason here is commutative. Then, number 5. So in number 5, it just became P. So how it happened, what number it came from? It came from number 4. Because number 4, kung makikita nyo, P and Q. So P and Q, yung number 5 na isolate na lang siya, naging P na lang. So pag nababawasan, anong rule yun? Simplification. So the reason here is simp. The number 6, therefore Q. So we will prove now our given formula at the left side, modus ponens. What number it came from? 2 numbers. Let us find the premises. It came from numbers 3. Here's your number 3, P, then Q, and number 5. Reason, MP. Number 2. Modus tollens. Abbreviation MT. The formula is if P then Q, not Q, therefore not P. So we have here two premises which is equal to our one conclusion. Let's give an example. We have here given premises numbers 1 and 2. So we need to prove from 3 to 6 by writing the correct rule taken from rules of replacement and rules of inference. So number 3, how it happened if P then Q. So in number 3, it is taken from number 1. What rule did we apply? We apply transposition. Trans. And then number 4, if you will notice, number 4 is just the order changes. It came from number 2. So in number 2, you can see not P and not Q. In number 4, you can see not Q and not P. So they just change in terms of order. So from number 2, when we're talking about order, we are referring to commutative rule. The number 5, so not Q became isolated, just a single proposition. So it came from number 4. So we simplify number 4 by removing the proposition at the right. So we apply simpt. Then number 6, proving modus tollens. At the left side, we have find the two premises. So the two premises from number 3 and number 5. Reason, modus tollens empty. Number 3, hypothetical syllogism. HS. If you have if P then Q, if Q then R, therefore if P then R. As you notice in our given rule, it's like we can cancel Q here, applying transitive property. That is our hypothetical syllogism. Let's give an example at the right side. If I have A, if and only if B, then not T, and therefore A, if and only if B, then R. So what's the missing statement at the middle or in between applying this rule? Hypothetical syllogism. As you observe our given, this A, if and only if B, is just equivalent to P taken as 1. And this not P is your Q. This one below, in our conclusion, is still equivalent to P taken as 1. And our R here is still our R in the formula. So what's the missing at the middle? So at the middle, what's missing? What's the formula here at the left? The formula here at the left is Q then R. So what is our Q? Our Q is not P. Okay? Then, what is our R? So, our R is the same as R. So, this is the answer. Number 4, disjunctive syllogism. Abbreviation or acronym that you're going to use when you prove VS. Given by the formula P or Q, not P, therefore Q. Let's give an example. Number 1. So we have premise number 1, not P and not Q. Then premise number 2, not Q and not P. So how we came up with number 3? How this happened? It is taken from number 1 and you applied De Morgan's. Okay, so in De Morgan's, you will just distribute the not and the symbol will be changed. If that is N, it will become OR. So for number 4, it came from number 3, double negation. So in double negation, if we have not P, that is just equal to P. So we applied double negation twice because we double negate not P becomes P and not Q becomes Q in number 4. Then number 5, it came from number 2. Just interchange or change the order. Commutative. Then number 6, so we subtracted. So it just became not P. It is taken from number 5 by simplification. 7, we will now prove our formula at the left side. Disjunctive syllogism. We have 2 premises. Let's find P or Q from number 4, and then another premise, not P, and number 6, reason, DS, disjunctive syllogism. Number 5, constructive dilemma. CD. The formula is if P then Q, and if R then S, P or R, therefore Q or S. Let's give an example. This time, the statements are missing. So we need to supply the missing statements. Let's start with number 4. So it said here, the reason is from number 1, trans. So the equivalent of number 1 is if P then Q. Refer to the formula for trans in rules of replacement. Number 5, from number 2, material implication. So refer to the rule. So number 2, not R or S, is equal to if R then S. Number 6, from numbers 4 and 5, conjunction. So when we say conjunction, we use the connective N to connect two or to combine 2 statements. So copy first number 4, if P then Q, then copy number 5, if R then S. Then number 7, from number 3, add. So what we're gonna add to R? So in our left side, constructive dilemma, we can just add if we're using the symbol OR. So to have P or R, we need to add P to R. So R or P. Then in here, in constructive dilemma, it's P or R. So it says in number 7, commutative. So change the order. It will become P or R. And we can prove now constructive dilemma number 9. It's from number 6 and 8, constructive dilemma. So here is the conclusion. Therefore, Q or S. That's constructive dilemma. Number 6, absorption. Abbreviation, ABS. Given by the formula, if P then Q, therefore, if P, then P and Q. Let's give an example. Number 1, Q or not P. So that's our given premise. What is the missing statement in number 2? So it says here in our rule from 1 commutative. What we're going to do, just interchange this number 1. It will become not P or Q. The number 3, it says here from number 2, material implication. So what's the equivalent of this in material implication formula? So the equivalent of number 2 is if P then Q. So now we can prove absorption here at the left side. So therefore, if P, then P and Q.